Diffraction grating question 1. A narrow beam of white light is passed through a diffraction grating and gives the following angles from the normal. You'll see for the red light there is a first and second order, but no third order. The blue light is diffracted through smaller angles, as you would expect, as blue has a shorter wavelength than red. And also the third order of the blue is actually going to be inside the second order of the red. For part A, we're asked to describe the appearance of the complete pattern, maybe including a diagram. There's 4 marks for this, so quite a bit of detail expected. Well, I'm going to start with a diagram and then point out some of the main features. There is a white band in the centre where all the colours come together, and the pattern then spreads out from there, being symmetrical on either side, with the blue diffracted the least, the red diffracted the most. The further out second and third orders are more spread out or more dispersed, and also more faint, as the energy is spread over a bigger area. Some of those main features then. The pattern is symmetrical with a white central maximum. It's blue on the inside, red on the outside. The dispersion increases and the pattern becomes more faint at the higher orders. And the third order overlaps the second order. I've shown this slightly above here just for clarity. Part B. If the wavelength of the red light is 680 nanometers, calculate the line separation of the grating for 3 marks. Well, from the datasheet we get that n lambda equals d sine theta, n being the order, 1, 2 or 3 in this case, lambda the wavelength of the light, d the line separation in the diffraction grating, and theta the angle of diffraction. It's d we want to find, so rearranging the equation we get d is equal to n lambda over sine theta. N in this case is 1, the first order, and the wavelength is 680 times 10 to the minus 9 meters. We got that from the question here, 680 nanometers. And the angle of red light for the first order we got from the table on the previous slide of 26.2 degrees. This gives a line separation of 1.5 times 10 to the minus 6 meters, or 1.5 times 10 to the minus 3 millimeters. Part C. Calculate how many lines per meter are on the diffraction grating for 1 mark. Well, the number of lines per meter is simply 1 over the separation of the lines, which we found in the previous part of the question. This must also be in meters, giving the number of lines per meter of 6.7 times 10 to the 5. This is a number and so doesn't need any units.